The problem with that is that you will end up using it only, so you put something, you wash something last, and you put it on top of the stack. So you are going to use it again, okay, and then you are going to wash it and put it back, okay, while and the life expectancy of your clothes in this case is going to go very down, okay. What you need to do is really when you when you wash your clothes, you want to put them back at the end here, assuming you have no preference. I mean, I don't have preference, so I just put them back here, okay. But if you have preference, that's another data structure. We will see it. That's called a priority queue. We will see it at the end of the semester. But here, the most relevant data structure, like for washing clothes, is to put them in a queue. So when you finish with something, you put it at the beginning here. So it's not a stack. Okay. So that was just a question for you. Now we are going to see what a stack is. Now, before talking about the code, so this is how a stack is. First, it's just some sort of a container. That's a stack, and we add elements to it. When we say add elements in stack terminology, it means push. Okay, so we push an element A, and this is what we get. It's the same container with the element A inside it. And then we want to push another element, and it's the same container with B on top of it now. And so on and so forth. And here we push C. Now I want to remove an element. Removing an element, in this case we call it pop. Okay, so when I say remove, I say pop. When I say push, I need to specify the elements. So I say push A, push B, push C. But when I want to remove, I just say pop. I don't say I don't say the name of the element. Now why? Yeah, there is only one element to remove, right? Which is the one on the top. So I don't need to say remove, because I can only remove the one at the top. So if I say remove, it's going to be C anyway. Here it's going to be B anyway. So this is why we don't need a parameter for pop. Again, I want to put something new. So I push D, and this is what I get. These numbers here are just numbers, state, so that when you watch this slide, you understand the ordering. Now, so now we know what's going on. When we put an element, when we put the first element in the stack, this element is going to be at address or at index 0. Okay. We can also agree to make it at index 1, but I just element is going to be at address or at index 0. Okay. We can also agree to make it at index 1, but I just try to sometimes start with 0, sometimes start with 1, so that you don't get stuck just in one indexing scheme. Okay. So here the element, or when we put the first element, it becomes in or it is stored at index 0. When we add another element, it becomes on, or it is stored on top of that, so it's 1. When we add a third one, it's on top of that, and it's 2, etc. Okay. Now when the stack is empty, before stack is empty, this is called the top element, which is the element which is the top of the stack. So here the top element is A, and here the top element is A, and here the top element is B. Okay, the top element is B. Okay, the index of the top element is 1. Yes. Okay. Here the top element is B, and the index of the top element is 1. The top element is C, and the index is 2. The top element is C, and the index is 2. The top element is D, the index is 2. And here the top element is A, and the index is 0. Now, When the stack does not have anything, we are going to use top equals -1. Okay, this is to signal that the stack is empty. So stack doesn't have anything. Okay, now if the first index was 1, this will be top equal 1. How do we say the stack is empty? Top equals 0. Yeah, we can say by top equals 0 if the first element of the stack or the bottom element of the stack starts at 1 instead of 0. You have question? Okay, good.
I'm going to code using stack as well. So I will how I can order the stack.
How you can order?
Yeah, how can order it? How can order the element? I don't know when I can order to 0 and when to 1. You said right
Yeah,
now,
I said right now what?
the first element may we start by 0 or 1.
Not exactly. I said, okay, in this example, we are assuming that the first element, when we put the first element of the array, it is going to be at position 0. This is because at the end, a stack is just an array. Okay, so stack is just an array which looks, instead of being flat, it is vertical. Okay, so arrays start at 0 or they can start at 1. 2, 3. So I'm saying in this example, 2, 3. So I'm saying in this example, I am assuming that the first element of the array is starting at 0. However, we could have written the example differently by saying that each element starts at 1. So this becomes 2. But these two are two different examples. The first element of the stack is going to either be 0 or 1, and this will depend on what I tell you. It's not something you figure out yourself.
Yeah.
No, I'm not sure if this was an answer to your question.
Yeah, it is, but I was a bit confused about how I can figure out if I will start with 0 or 1.
This is something. It depends on your programming language. For example, if you're using Ada or Pascal, I think Pascal as well starts indexing from 1. Okay, so in this case, you are going to have your stack start at 1. If you're using Java, you will start your stack at 0. Okay,
Yeah.
so it's a programming issue. It's not a big issue. So now we know what is a stack. It's a container where we push elements and we pop elements. The element that we put last is the one that we get first, and the element at the top is the most important element, and we call it the top of the stack. Okay, so we said here, B is the top of the stack, and the index is 1. Okay, so top, this top here is not an element, it's an index. This is a common mistake. When I say, what is the top of the stack? You say it's B. Okay, now what is the index? In that case, it's 1. So the top of the stack is an element. The top of the stack is an element. It's like B. Okay, so now we know how a stack works. So now we can understand the code behind it. So a stack is called LIFO, last in, first out. So the last element that comes in is the first one that we can get out. Okay, last in, first out. So the stack is a container which looks like that. This place here is fixed; it doesn't move, and the place here moves. So when we add element, the top index is going to grow. When we remove elements, when we remove elements, the stack is going to shrink, and we draw it vertically. right? So instead of horizontally, that's just a convention. I mean, if you draw it like that, I mean, you're free. But that's just a convention that we draw it vertically, and it grows from bottom to top. And the operations in the stack are push, which adds an element on top of the stack. Pop, this is to remove and return. Okay, so in my explanation so far, I told you pop, we are going to remove C. Well, pop is not delete. We are not going to delete C. We are going to remove it and return it to the user. So when I say pop, the pop of some stack, you basically return the top element to me. You remove it, yes, and you give it to me. You don't just throw it away. It's not delete. Okay, so pop is not delete. You have to return. So pop removes the top element and returns it to me. Now peek, you are going to return the element without removing it. So if I say peek, if I say here peek, what happens? Okay, so after that, the stack is going to look exactly the same, right? Okay, so this is peek. We are just looking. Is empty is just a Boolean function. If the stack is empty, then it returns true. How do we implement that? How do we know the stack is empty? Yeah. So if top is -1, I mean, assuming start at 0, okay? If top is -1, then stack is empty. Is full. So this is something I did not explain. A stack, obviously, a stack is going to be an array, and it can grow. However, it can only grow up to a maximum size. So we can add elements as much as we want. However, at the beginning, we have to specify what is the maximum number of elements we can add. We cannot make it infinitely or grow infinitely. We cannot do that. Okay? So, for example, I can have a stack and say the max size of that stack equals 20. So I can only add 20 elements. So I can add and pop, push, pop, or in the maximum, I can only push 20 elements in a row. Okay, one after the other. I cannot do more than that. After that, the stack is going to be full. Okay? So if max equals 20, and if the stack starts at 0, how do we define the procedure, the function or the method is full? Top equals max -1. I don't hear you. Okay, in
Just for like the last index, that we have.
so okay, so if the max size is 20, it means we can grow from 0 to 19, right?
Yeah.
So what does it mean to be full in this case? Is that top equals? Okay, I was dead right. So, and then size. Now size returns the size of the stack. It doesn't return the maximum size, okay? The maximum growable size is 20, which is how big the stack can be in the maximum case. Now size is going to return to me how big is the stack right now. Okay? So basically I need some space to draw. So this is our stack. This is the max. Max is 20, and we have elements A, B, C. So what is the size of this stack? Exactly, 3. So how do we implement that? So size, how do we implement it? By computing what? Top? Yeah. So if we start from 0, it's going to be top plus 1. If we start from 1, it's going to be top, right? 1, 2, 3, or 0, 1, 2. So it all depends on the indexing scheme we're using, okay? So when you get questions like this in exams, always make sure you are paying attention to the indexing scheme. Am I starting from 0? Am I starting from 1? So what am I saying here? Stacks. Dun, dun, dun. Yeah, stacks. When do we finish? 11:30. Right. So, I just want to explain what I am saying here. So stacks are used by the operating system to handle recursion and procedure calls. Now, what does that mean? It means the following. I don't mean you. Okay. Right. So when you write a function, let's say you have a program P1 and program P1 calls program P2 and program P1 calls program P2. So basically you have method. Let's use method. So you have a program. It's one program. And you have functions inside this program, or methods in Java terminology. So you have function 1. Function 1 does something. Okay, so there is some code, blah blah blah, and then calls some other function, function 2, and then finishes. Okay, and then function 2 does some code and calls function 3. Now, so basically what happens, we have F1 calling F2, and then we have F2 calling F3. Now, when the processor tries to execute this function, what it does is, now when it executes, so function 1 has got variables like x and y, for example. Function 2 also got variables like x and y, and function 3 got variables also like x and y, and they are all inside their own scope. Okay, so what happens is the CPU is executing F1 and then until here, and then it needs to call function 2. So what it does, it creates a stack. It puts here the variables which are basically it's the state of function 1. We call it the state of function 1. Different variables, the results that we have computed so far, because we have only one CPU. And when we start executing the next instructions on it, like from function 2, then the previous instructions are completely deleted. Okay, the results that we have used in function 1, they are in registers inside the CPU, and then function 2 comes in, uses the registers, and we lose the results of function 1. Okay, so this is why before we go to function 2, we need to save the state of function 1. So we use a stack. So we put the state of function 1 inside the stack. And then we move to function 2. And we execute function 2, and then we need to execute function 3. We need to call function 3. So before doing that, we are going to put the state of function 2 inside the stack so that we don't lose it. And so we call function 3, and we execute everything, and we're happy, and we are finished. So when we complete the execution of function 3, we go back to this point. In this case, we pop the state of function 2 because we don't know how to execute the remaining instructions. We might need something like y equal x plus 1. Now what is x? Where is it? This is why we are going to pop it from the stack. Now we have the data that we need to compute. So we pop, so we give it, we return it here, and basically we remove it from here. And then we finish executing f2. After we finish executing f2, we go back to where we have called it from within f1. Now, again, we have something like y equals 2x, where we have called it from within f1. Now, again, we have something like y equals 2x. Now, where is 2x? What is x? So we go and get it from the stack. This is the state. That's the state of our function. So we get this, and we pop it, we remove it, and we use it here. So this is what I mean by the stack is used by the operating system in order to organize procedure calls. So these are procedure calls. We are calling a procedure from another procedure. And the same thing happens if you have a recursive function like factorial. So factorial of n, and then calls factorial of n minus 1. Before going there, you are going to save the state of your factorial first, and then n minus n, etc. Each time you make a new call, you are going to push a new element in the stack. Then when you compute the base case of your recursive call, you start popping and coming back until you compute the final value of the recursive function or of the factorial function. This is why sometimes when you have a recursive function, when you implement it, you execute it, and you give it large values, your compiler or your program crashes and say there is not enough stack. It says something, there is no enough stack, because your function takes a huge parameter and always needs to push a new state, push new state, but then you run out of memory and your program crashes. So this is the stack that your program talks about when it crashes. Okay, back. So again, we are in stacks, and we have talked about the different operations, and we have already talked about how we do the pushing, etc. So what we said, well, a stack is an array. So if a stack has maximum stack size, we are going to declare it as an array s from 0 to max stack size minus 1. Okay, so this is our stack. That's the real maximum here, and it starts from 0, and it's going to end at max stack size minus 1. Top. We said that top is the top element, the index of the top element. S of top, we said S is the stack, right? S is the array. So this array is called S. Now, so top is the index, S of top is the top element, okay? So there is a difference. Index of top element and the top element itself. Now pushing is basically just saying S of top equals X. It's very simple. Okay. However, we do that after we increment top. Okay. So right now we're here. We have A and B, and the top is equal to 1. So top is 1. Now, in order to push C, what we are going to do, C is going here. So we increment top by 1. So we make top now equal 2. And then S of 2 equal what? S of 2 equal what? I said I want to push C. So S of 2 equals C. So S of 2 equals C. So C is pushed this way. So this is what we mean by push. Increment the top index and then make the array or the stack equal to the new element at that new value of the top index. Okay, so increment and then do that. Now pop. What is pop again? So okay, so pop. So we have A, B, and C, and we want to pop. So what we do is we want to return C and remove it. So what does it remove? What does remove mean? All we have to do is the top first was pointing here. All we have to do is to decrement top, make it point here. So B is the top element. C is still there, but for us it's a garbage value. Okay, so for us we don't care about it. Before decreasing the value of top, obviously we have to store C in some temporary variable. So we have to say something like x equals C. We store it inside of x, decrement top, and then return x. Because if we decrement before, we have lost C already. Okay, so we have to store the value first and decrement it later on. Now peak is easy. We just return S of top. Is empty, we check if top equals -1, and is full, we said we check if top equals max -1. So this is what we this is stack in operation, and now we move on to queues. I just need 1 minute to take my breath. Okay, I've used my minute. Now queues is our next topic. A queue is very, well, it's not similar to the stack. So okay, I've used my minute. Now queues is our next topic. A queue is very, well, it's not similar to the stack. So let's visualize what is a queue. Okay, again a queue, we can think of it as a stack. We can think of it as an array. Okay. Okay, let's not think of it as an array. Let's think of it this way. It's also a container. This container, I mean, not like the stack. It's horizontal. Okay, so it's not vertical. I hear a lot of noise in the class. So a queue is we think of it as a horizontal container like this. However, it's not like the stack. It's open-ended. Okay, so it's not closed. Now the queue is just like human queues. When it's how basically people come from here and go out from here. So there is this guy. The guy called A is going to come here. Is the first guy. He or she is waiting in the queue, and then another guy comes in. B is going to be waiting before A, and then C comes, and C is waiting after B. Okay, And then there is the guy here. He's calling A. Now A come over here. Now A goes here and is removed from the queue. Okay, and the guy now calls B, come over here, and B goes towards this guy and is removed from here, and so on. So a queue has two parts. There is an entry part like this, and there is an exit part like this. So this one is called the front of the queue. So this is the front. The person who is first in the queue will be standing here, and the person who is the last in the queue will be standing here. So this is the front, and this is the back of the queue. So front of the queue and back of the queue. And we said that people move from here, or items move from here to here. In order to add something to the queue, okay, so when we say in queue A, what we are doing is we are adding an element to the queue. So we are saying A has been added to the queue. When we say in queue B, we are adding B after A. So A is first. When we add B, B is to the left of A, and then we in queue C, and C becomes to the right of B. Sorry about my directions. A, and then B behind it, and then C behind B. When we say DQ, okay, so there is in queue for adding elements, and DQ for removing elements. Okay, so we have been in queuing things, and then when we said DQ,